Welcome to another video. Let's walk through this physics challenge on the board. What is meant by the root mean squared value of an alternating current? Define impedance of an alternating current circuit. An electrical device rated 120 volts, 60 watts is operated on a 240 volt, 50 Hz main supply. The circuit has a capacitor connected in series with the electrical device and the supply. Our task is to calculate the capacitance of the capacitor. So the last question is for us to define the capacitance of a capacitor. Okay, now what is meant by root mean squared value of an alternating current? Root mean squared value of an alternating current is also known as effective value. Okay. Now, when we talk about alternating current is a current which first flow in one direction called positive direction and then in reverse direction or negative direction. Okay. All right. So root mean squared value of an alternating current is the effective value of alternating current in a circuit, or it can also be defined as the value of a steady state or DC current, that is direct current, okay, which produce the same heat in the same time in the same conductor. So that's in the case of root mean squared value of an alternating current. That is a solution. We have root mean square value of an AC, okay, of an AC is the effective value of an AC, that is alternating current, in a circuit. That is, it is the value of a steady state current. It is this value of a steady state current or direct current, which produces the same amount of heat, in the same time, okay, in the same conductor. So this is one of the many ways to define root mean squared value of an alternating current. But as the question goes, what is meant by root mean squared value of an alternating current? Okay, it also means effective value of an alternating current. Okay, is the same as the value of direct current. Okay, you know I said AC current, that is alternating current, is a current which first flow in one direction called positive direction, and then in another direction called negative direction. So when we have the value of an alternating current to be the same as the value of a direct current or a steady state current, that is the current flowing in one and only one direction, okay, which produces the same amount of heat, okay, in the same time in a conductor, then we have what we call root mean squared value of an alternating current. Okay, then B, we also have impedance. Define impedance of an alternating current. As the word implies, impedance, restriction, okay, hindrance, opposition. So impedance measures the total opposition to the flow of alternating current in a circuit, or we can say the total opposition or restriction or hindrance to the flow of alternating current in a circuit. That's why we have what we call capacitive reactance, inductive reactance, and also resistance or impedance. Okay, All right, and we can also define impedance in terms of measurement as the ratio of peak value of voltage to the peak value of current, okay, in an AC circuit, or the ratio of RMS value of voltage to the RMS value of current. So like I said, impedance is defined as the total opposition, in ohms, okay, in ohms, to the flow of an alternating current, to the flow of an alternating current in a circuit, in a circuit, to the flow of an alternating current in a circuit. All right, so in measurements, let me add this, okay, this is another way to answer the question, okay. In measurement, comma, impedance can be expressed as the ratio of the peak value of voltage, the peak value of voltage to the peak value of current, to the peak value of current, to the peak value of current, okay. Or it can be measured as the ratio of RMS value, that is root mean square value of voltage, to the root mean square value of current. Okay, so in this case, now impedance can be denoted by letter Z. Okay, we use letter Z, okay, to represent impedance. So impedance equals to peak value of voltage over peak value of current, or it can also be measured as the ratio of root mean square value of voltage to root mean square value of current. Okay, so this is peak value of voltage or amplitude voltage divided by amplitude current. Okay, you know the maximum value of voltage in the AC signal is what we call peak value of voltage, and also the maximum value of current in the AC signal is also known as what? The peak value of current. Okay, all right, so the unit of impedance is the ohms, so that's why impedance is defined as the total opposition in ohms to the flow of an alternating current in a circuit. That's it. All right, so C, an electrical device rated 120 volts, 60 watts is operated on a 240 volt 50 hertz main supply. The circuit has a capacitor connected in series. So this is where we have a connection, a series connection of resistance, okay, as a resistor will be connected to a capacitor in series in an alternating circuit. Okay, but the first thing is that we have an electrical device rated 120 volts, 60 watts, and it is operated on a voltage source of 240 volts at a frequency of 50 hertz. Okay, so this is the AC source. Okay, I'm going to draw the circuit diagram. So the first thing is we need to first calculate the current drawn. Okay, that is the current drawn from the main, okay, by the rated, that's the rated current. Let me call it the rated current. So the first thing first, okay, is to calculate. So we have voltage, we're giving voltage, that is for the electrical device, So we have voltage to be equals to 120 volts, then power, the power rating, okay, power rating is equals to 60 watts. So which means rated currents, okay, rated currents is what we need to first calculate. So rated current will be equals to, because power is equals to the product of current and voltage. So it means if we express current in terms of power and voltage, then we're going to have rated currents. The rated current will be equals to the power rating over voltage. So in this case, the rated current will be equals to 60 divided by 120, and this will be equals to 0.5 amps. So which means that the rated current is equals to 0.5 amps. Okay, now like I said, the device, okay, I said we're going to have an AC circuit containing series connection between a resistor and a capacitor. So which means we need to calculate the resistance. So to calculate the resistance, I'm going to use this guy to calculate the resistance. Alright, so we have the voltage to be 120 volts. We have the current to be this, okay? So next, we need to calculate resistance. So resistance R. Resistance R will be the rated voltage divided by the rated current, so that resistance will be equals to, the rated voltage is 120 while the rated current is 0.5. So this will be 240 ohms. So which means that the resistance is 240 ohms. The resistance is 240 ohms. Nice. Now, we just calculated the resistance, and we are given that this is the supply voltage. So it means that we have a circuit containing series connection between a resistor having a resistance of 240 ohms connected to a capacitor. Okay, so this is resistor. The resistor is 240 ohms. 240 ohms. 240 ohms. Then this is the capacitor. So this is now connected to the what? The main, that is AC source. And the voltage source is 240 volts, while the frequency is 50 hertz. So we have the current leaving the main as I, okay? And like I said, they are connected in series. And we know that for series circuit, okay, we always have that the component connected in series, we have different voltage drops, okay? So the voltage drop across the resistor will be VR, okay, will be VR. And the voltage drop across the capacitor will be VC. Okay, so which means that the voltage source, in this case, the voltage source, okay, the voltage source, we are going to make use of the formula. We're going to have this is the voltage across the resistor, okay, plus, then we have on the y-axis, we're going to have the voltage across the capacitor. I think this should be upside down, or so we're going to have the effective voltage, which is the voltage source. So if I'm using Pythagoras theorem, so this is the voltage across the capacitor. So which means from here, we're going to have the effective voltage to be equals to square of effective voltage to be equals to VC squared plus VR squared, where V will be equals to square root of VR squared plus VC squared. So we need to calculate the voltage across the capacitor. So for the voltage source, so from there we have V squared equals to VR squared plus VC squared. Okay, so which means that this will be V squared, that is the voltage source. The voltage source is 240 volts, so raised to the power of 2. Then the voltage across the resistor. The voltage across the resistor will be, when we multiply 0.5 multiplied by 240, okay, that's the voltage across the resistor. So the voltage across the resistor will be 240 multiplied by 0.5, and that will be 120. So this will be 120 squared, then plus VC squared. So that this will be 240 minus 120, because we're going to have difference. Okay, let me write it as a difference of two squares, so that from here we can have 240 minus 120, okay, 240 minus 120, okay, multiplied by 240 plus 120, and this is still equals to what? VC squared. So 240 minus 120 is 120. So I'll have VC squared to be equals to 120 multiplied by, this will be 0, 6, this will be 360. This will be 360. So from here, we're going to have VC to be equals to square root of 120 times 360. 120 multiplied by 360. That's 43200. 43200. Okay, so the square root of 43200. So this will be, VC will be equals to 207.8 volts. So this is the voltage. This is the voltage across the capacitance. Now we need to calculate the capacitive reactance. So the voltage across, to calculate XC, that is capacitive reactance. Capacitive reactance. So we know that voltage across capacitance will be I times capacitive reactance. And let's not forget that in a series circuit, the same current will flow through the entire circuit combination. So in this case, we're going to have our VC is 207.8. Okay, this will be equals to 0.5 multiplied by XC. So where XC will be equals to 207.8 divided by 0.5. So it's just to multiply the value by 2. That will be 415.7. So XC will be 415.7 ohms. So this is the capacitive reactance. Okay, so our task is to calculate the capacitance of the capacitor. So to calculate the capacitance, okay, of the capacitor, so we make use of XC equals to 1 over 2 pi FC. Remember, we are giving F to be 50 hertz, so F equals to 50 hertz. Okay, C, we need the value of C. Then we have XC to be equals to 415.7 ohms. So I'll plug in the values here. So this will be 415.7. 415.7. This will be equals to 1 over 2 pi multiplied by 50, because the frequency is 50, okay, multiplied by C. So when we multiply this, okay, making C the subject of the formula, C will be equals to 1 over 415.7, okay, then multiply by 2 times pi. We are given the value of pi to be 3.142, then multiply by 50. So this is 100. Multiply by 3.142, that will be 314.2. Okay, so this will be multiplied by 314.2, because 100 times 3.142, that will be 314.2. Okay, so 415.7 multiplied by 314.2, that will be 130612. So we have this to be 1 over 130612.94. So when we divide the value 130612, okay, 0.94, when so 1 divided by 130612.94, that will be, so we're going to have C, the capacitance, to be equals to 7.66, okay, times 10 raised to the power of minus 6 farad. So if you approximate this to the nearest tenth, then this will be, capacitance will be 7.7 microfarad. So this is the capacitance of the capacitor. So the last question is for us to define the capacitance of a capacitor. Okay, capacitance of a capacitor, okay, can be defined can be defined as the ratio of charge per plate of a capacitor, charge per plate of a capacitor to the potential difference between the plates. That is the plate of the what? Capacitor. We all know that capacitor consists of two oppositely charged parallel plates. That is, one plate carries positive charge while the other plate carries a negative charge. Okay, so capacitance of a capacitor can be measured or can be defined as the ratio of charge per plate of a capacitor to the potential difference between the plates. The noblest pleasure is the joy of understanding. Bye-bye.